Welcome to this video about the marginalized particle filter, the MPF. The MPF is a well-known algorithm that goes under several different names. So sometimes you hear about it as the Rao-Blackwellized particle filter due to its connection to the Rao-Blackwell theorem, or the mixture Kalman filter due to the connection to stochastic filter banks. The idea behind the algorithm is to reduce the number of particles needed in the particle filter by utilizing underlying structure in the estimation problem that's being solved. I'll give some intuition for the algorithm, but we'll refer to the textbook for the details about the equations needed. To fully follow this video, I recommend that you first study the particle filter so that you know the basics of that. To set the stage for the rest of this presentation, we'll review the particle filter. So it's a method to do filtering on nonlinear models of this kind here. So any nonlinear model, we don't make any assumptions of the distribution of the noise, so it doesn't have to be Gaussian, for example. The idea is to sample a large number of particles or samples from the initial distribution, and then in a two-step procedure, more or less at least, incorporate measurements to tell which of these particles fit our estimation problem well, and to propagate them forward in time using simulation. So we get this normal filtering two-stroke process where we include measurement data and we propagate things forward in time to see what happens in the future. Two additional steps are needed. We need to normalize the weights that the measurement update gives rise to, and we need to resample. The resampling step is to make sure that we have particles supporting the solution of the problem. If we don't do that, we'll deplete the Kalman filter and get no sensible result. It should be noted that for the particle filter to work well, we could end up needing a lot of particles, especially if the state space is large. And this is a problem in practice when we need to run things in real time. And that's what the marginalized particle filter will try to address. So the objective here with the marginalized particle filter is to decrease the number of particles needed to support large state spaces. And by large state spaces, we talk about things with larger dimensions, let's say 3. And we can do this in cases where there's a linear substructure of the problem that's Gaussian. And to give some intuition why this is useful, so consider the filtering problem that we have that's nonlinear. There's two parts of it. The one is to represent the filtering distribution in a good way. For the linear Gaussian case, we just use a mean and a covariance, whereas in the particle filter, we need a lot of particles to represent it as a whole. The second step is to then propagate these distributions or the representations of these distributions forward in time. And in this case, the Kalman filter has an efficient way to do that with simple equations, whereas we have to deal with each particle separately in the particle filter. So if we could find the substructure in our problem where we can run the Kalman filter, we have a possibility to make things more efficient. So to see what I'm meaning here is that look at this initial distribution that we have here. It is non-Gaussian. Apparently, we have two different peaks, modes in the PDF. This is not well represented by a single Gaussian. If we want to do this with particles, we do something like this, if you see in the middle, where we have used a lot of particles that then gather to represent these peaks in the distribution to the left. We need a lot of particles to cover the whole area here to see where the distribution has its peaks. Now, it turns out that in this direction here, for each position in this direction, along this axis, we have a Gaussian distribution. And we can actually represent this in this more efficient way, where for each point or for a particle in this direction, we represent the distribution in this direction with the Gaussian. We can then have a few numbers of particles just representing this dimension and associate a Gaussian distribution with others. And we can solve for the Gaussian distribution quite easily, so we have a more efficient method. So let's formulate this in a bit more formal way. So what I'm talking about is models of this kind here, where I split it up in a nonlinear part of the state space and a linear part. And to highlight this a bit more, we'll color it. So the red part associates with the nonlinear things, and the blue part associates with the linear parts. The nice thing here is that if we condition on this nonlinear part, xn, the rest is a normal linear Gaussian model, so we can apply the Kalman filter. And given the statistics for the blue part, the rest is actually something that we can solve fairly easily with the particle filter and with a lower dimensional particle filter. So what we'll do from now on is to try to define this method that deals with the linear part with a Kalman filter and the nonlinear part using a particle filter. These kind of model structures are not that uncommon. In most navigation, tracking, and SLAM problems, we turn out with this kind of model structure where the position itself is the nonlinear part, but velocity and accelerations that we might have in the state usually turn out to be linear. I'll exemplify this with the 1D terrain navigation example, and this is the same example more or less as you've seen before for the particle filter. The thing here is that we measure the distance down to the ground from the thing that we want to position, and we, by having motions here, can see that if the distance down to the ground changes in a certain way, we can only be in a certain position. This is a problem that's highly nonlinear in the measurement, because this measurement of the ground based on the map is definitely not a linear function of the states. That makes the problem separatable in this way. So we have the speed being the linear part and the position the nonlinear parts. So this is exactly the kind of model that we've been discussing on the previous slide. Now trying to put all this together and solve things in Kalman filter and particle filter parts. Start by looking at these equations here. So we now condition on the position over time. We see that velocity here is linear dynamics, and given that we know the next position and the current position, which we can get from the particle filter, this is linear measurements that we can apply to the Kalman filter. So this part here becomes the Kalman filter part. The reminder, which is then this update of the position with this measurement that is nonlinear, becomes the particle filter part. Note that if we solve this part first, we have a statistics for this, so this can be then applied in a normal particle filter. And this particle filter is just one-dimensional instead of two-dimensional. By running these Kalman filters and the particle filter, we now get the representation of the posterior distribution as I described previously. That's a mixture between Gaussians and particles. Now let's generalize this a bit. So the key here is to divide the state space into two parts. So X is the full state space, then we have Xn, that is the nonlinear part, and XL, the linear part. And given the model structure that we have, conditioned on this part, this thing here will be linear, so we can deal with it. That means that we can divide or factorize the posterior distribution, which is the probability of XL and XN given all the measurements in this way here, where we have one part that is the distribution of the PDF of XL given the XNs and the measurements, times a part that is only the probability of XN given the measurements. This first part here is, as I've said now a couple of times, linear and Gaussian, so we will apply the Kalman filter to that, whereas the second part can be handled with a particle filter. I'll outline how this is done in the next few slides. I'll give the intuition, but you'll have to read the textbook for the exact equations to actually perform this. we can view this as a stochastic filter bank, which is a kind of a nice interpretation of the whole algorithm. So we'll start by the conditional Gaussian linear part of the problem. So this PDF up here. I have rearranged the equation slightly. So we have this part here, which is the update of the linear part, which is then given that we know the orange part or the red part here, linear and Gaussian. We have a measurement here. So given again the red parts, this is a linear equation that you can solve using the Kalman filter. And then we have this, which is actually the update, the time update of the nonlinear parts that we can deal with as a measurement update if we have also the next time step of the nonlinear part. So to summarize that a bit, we'll use equations KFTU and KFMU1 in a normal Kalman filter, one for each particle that we have. Once we actually obtain new particles for the next step, we will then use this last equation, the KFMU2, as another measurement update in the Kalman filter to compensate for the exact choice of nonlinear state that we did in the particle filter. Note that we need to run one Kalman filter per nonlinear state combination that we want to consider. This can be slightly expensive, but in many cases we can reduce the computational complexity by using a little bit more structure. So for example, if the uppercase matrices up here in the model, if they are constants and don't depend on xn here, then the p and the k in the Kalman filter, so the Kalman filter gain and the covariances, do not depend on the exact particle, so we can compute them once and for all. And we only have to update one state mean per particle, which could be quite inexpensive. So it's now time to deal with the remaining part of the state space, the part that is dealt with a particle filter. And that corresponds to this last factor in the factorization. And if we rearrange the equations in the model again a bit, we end up with this thing here. This is a normal time update in a particle filter, if you want, given that we know the statistics of XL, which we do from the Kalman filter part. This second equation don't tell us that much, but the last one is a measurement update. Again, we use that we know the statistics of XL. So we can make a normal time update with the PFTU equation. We utilize the distribution from the Kalman filters. We then can make a measurement update using this PFMU equation, and then perform normal resampling when necessary. Note that the resampling then of course chooses the matching Kalman filters with the particles. The handling of the second factor in the factorization of the posterior distribution using a particle filter can be viewed as a stochastic generation of trajectories and pruning of them in a Kalman filter bank. And that's the reason for the name mixture Kalman filter that's sometimes used. I encourage you to compare these steps to the Kalman filter bank steps. In that case, we have a discrete valued state space for what we call the nonlinear part here. We can enumerate all different possibilities and then have to reduce them based on probabilities. That is exactly what we do here. The only difference is that we have a continuous part, that's the nonlinear part, and that we use the particle filter to choose which parts to keep and what trajectories to throw away. This concludes the description of the marginalized particle filter. If you want to have the exact expressions for all these steps, which turns out to be slightly involved, please have a look in the textbook. The marginalized particle filter has several properties that makes it beneficial compared to the particle filter. for many problems. One of those is that it requires fewer particles to give good support for the solution. And this is due to the fact that we actually use Gaussian distributions to represent dimensions of the problem that can analytically be described by Gaussian distributions instead of using particles. So we save particles there. This can be utilized in several ways. So we can either use fewer particles and get the same variance in our estimates as we would do with the particle filter, or we could use the same number of particles and instead get a better estimate than we would with the particle filter. Due to actually having an analytic solution for part of the problem, we have a lower risk of a divergence, which simplifies the problem, of course. And since the particle filter part turns out to be easier than for the full problem, it's fewer tuning knobs that are really critical. So it's easier to choose the importance, density, and the resampling step, for example, so that's optimal. The price we pay for this is to have an algorithm that is more complex to implement. So this is a trade-off here. Is it worth adding some more complexity to get this, or is it better to run with the particle filter? It's up to each situation to judge that, but in many cases, this is a good alternative. To summarize, we have looked at the marginalized particle filter, which can be applied to nonlinear problems with linear Gaussian substructure. I've given some intuition for how it combines Kalman filters and particle filters in a filter that can provide higher accuracy than the particle filter using the same number of particles, or can be run with fewer particles without diverging. It, in that way, improves the robustness compared to the particle filter. The downside here is that it's a more complex algorithm to implement. An interesting aspect of the marginalized particle filter that I've been looking into quite a lot is that it can be viewed as a filter bank of Kalman filters with stochastic branching and pruning. I think this gives additional insights into the problem and also to the solution that it provides. I hope you find it interesting as well. To read more about this, I suggest having a look at section 9.8 in the textbook, which covers the marginalized particle filter.